So today we're going to be finishing up our discussion of carboxylic acid derivatives, but also introducing our next and last functional group of the course. And these kind of go together, so it's good to put them next to each other here. We're going to be discussing amides and amines. All right, so the amides are one of our carboxylic acid derivatives where we have that electronegative nitrogen bound to our carbonyl carbon, and an amine does not contain a carbonyl group, right? So that's our functional group, our nitrogen functional group with no carbonyl. Okay. For amides, one of our carboxylic acid derivatives, we talked about how we can convert carboxylic acid derivatives, the more reactive ones, into those less reactive ones. The amide was our least reactive carboxylic acid derivative. All right, but we discussed how when we do this reaction here and we add in that nucleophile, we have a problem. We actually don't make our amide product. What reaction happens between a carboxylic acid and an amine? Not that nucleophilic substitution business. Acid-base, right? Just an acid-base reaction. We said that you can sort of make this reaction occur by blocking up that carbonyl group using this catalyst called DCC. All right, we looked at the structure of this DCC. This is important just because you're going to need to draw it in your homework, so please make note of what the structure of this molecule is. We got these two cyclohexane rings, and then the important part here is this nitrogen-carbon-nitrogen double bond going on here. This is this important feature of this molecule. All right, but using this catalyst, then we can get our reaction to proceed forward. Okay. Now, surprisingly, we can get this reaction to go in the reverse direction by using either an aqueous solution of acid or an aqueous solution of base. All right, and that's kind of surprising because this is converting something the other direction is something less reactive into something more reactive. All right, so let's just say our reverse reaction is not thermodynamically favorable. Under those standard conditions, all right, but nonetheless, this reverse reaction occurs. So why? All right, but we'll say, but does occur. Why? Okay, so two important things here. You talked in Chem 1B about predicting whether or not reactions occur by calculating those delta G values. You can use those tables in the back of books, and those delta G values would tell you whether or not the reaction is favorable, but under a very specific set of conditions called standard conditions. All right, and at standard conditions, one of the things about standard conditions is the temperature is room temperature. That's fine here, but it also implies that the concentration of all your reactants is the same, is 1 molar. And so one of the ways that we can get this reaction to go in the reverse direction here is because when we have reactions under aqueous conditions, there's about a 50 molar excess, at least, of water in there compared to your reactant. So just simple Le Chatelier's principle, you are increasing the amount of water so much relative to your organic compound that it helps push the reaction in that direction. All right, so why, first of all, we have a huge excess of water. All right, but there's another very important reason why this reaction goes in the other direction, and that is as soon as that carboxylic acid molecule is formed, it gets trapped. All right, so let's look at this reaction. We'll be more specific here. We're going to take our amide as our reactant since we're going in the reverse direction. And we're going to react this with water. Under these basic conditions. All right, and like I said, when that carboxylic acid is formed, it's going to get trapped. All right, what do I mean by that? How is this reaction going to get trapped over here on the product side so that the reverse reaction can't occur at all? Well, so first of all, if I'm at basic conditions, my product isn't going to be this carboxylic acid. It's going to be what? The carboxylate ion. All right, so if we carry out this reaction under basic conditions, it's going to get trapped over here on the product side, because what I create is not the carboxylic acid, but that deprotonated carboxylate ion. And as we discussed last class, as soon as you deprotonate a carboxylic acid, you're putting a ton of electron density on that carbonyl carbon, and so this is not going to be an electrophile any longer. So the reverse reaction can occur. All right, let's do the same thing, but now we're going to look at this reaction under acidic conditions, and we're going to see something very similar. All right, again, this reaction is going to favor that more reactive carboxylic acid. And again, that's because when it's formed, it's trapped over here on our reactant side. Under basic condition, over here on our product side. Under basic conditions, we said that that's because not the carboxylic acid, but the carboxylate is formed. Under acidic conditions, I will indeed form that carboxylic acid, but what's my other product going to be under acidic conditions? That amine is going to play the role of a base, and so I won't get my amine, my NH3, as my product. I'll get the protonated NH4 plus. And although an amine is a good nucleophile, a protonated amine does not have a pair of electrons and cannot play the role of a nucleophile. All right, so just like before, under basic conditions, we said, we turn that carboxylic acid into a carboxylate, which is not an electrophile. Likewise, over here, under acidic conditions, we make our protonated amine, or our ammonium, and this thing over here is not a nucleophile. So we can't have any of this reverse reaction occurring. All right, we will instead favor that less reactive carboxylic acid under both acidic and basic conditions. All right, so this is a little surprising based on what we learned last class about ranking all of these carboxylic acid derivatives from the most reactive to the least reactive. All right, this is actually going to be a reaction that goes back, but again, it's because it's a little bit more complicated, or I guess back to the carboxylic acid. A little bit more complicated. It's favored because one, you can have a huge excess of water in there to help push it in the reverse direction, but also it will get trapped as either the carboxylate or the ammonium, preventing it from going in the reverse direction. Okay, and so, like we said, our amine got protonated, right? That's because amines are bases. So let's take a look at basicity of these functional groups. All right, so amines are bases. We have not really formally introduced amines yet in this course. The one reaction that we have seen with them is that they are basic. They play the role of a base in a chemical reaction. All right, so if we just take an acid, we'll take a strong acid, like hydrochloric acid. Here's our amine. Okay, everybody take a second and give me my products of this reaction. I guess I got some lone pairs missing. All right, so now we have that protonated amine and our carbonyl group. Okay, so amines are bases, and we'll talk a little bit more about amines and their basicity here in a second. Let's talk about amides. Amides are not bases. Let's see if we can understand why that may be. All right, well, so first of all, an amide by definition has that nitrogen bound to that carbonyl group. Okay, so then everybody take a second, since we have this allylic lone pair, everybody take a second and draw me my other resonance structure of an amide. Right, that allylic lone pair can be donated to that carbon, carbonyl carbon, and that would kick that pair of electrons up onto that oxygen. All right, so these are these two resonance contributors of an amide. And when we do resonance, especially when we're drawing in our electron pushing arrows, we're making it seem like these electrons are kind of moving back and forth. Like maybe it bounces over here for a bit and then goes back over here for a bit. But remember, with resonance structures, both of these are true at the same time. And this is definitely the less stable of the two resonance contributors, but just because it's unstable doesn't mean that it doesn't matter. All right, and it's really important to the chemistry of these particular compounds here. What these resonance contributors are illustrating is that in an amide, the nitrogen does not have a lot of electron density. That electron density is being pulled through that carbonyl group onto that oxygen, that carbonyl oxygen. All right, so because of that, that lone pair really can't be a very good base, can't be used to deprotonate something because it's already occupied by that oxygen, right? That pair of electrons is being pulled through that carbonyl bond up onto that oxygen. And in order to be a base, you got to have some electron density. You have to have a lone pair, right? So because that nitrogen does not have a lot of electron density, our amide lone pair cannot act as a base. All right, so we're not worried about protonating our amide under acidic conditions. All right, so that's why when we were looking out up here, we said that on the product side, it gets trapped because now we have an amine that can be protonated. We're not worried about that happening over here on our reactant side under acidic conditions. Okay. The other consequence of these resonance contributors here has to do with this bond in our amide, this nitrogen carbonyl bond. We can see in our other resonance contributor, it's a double bond. All right, and remember, big difference between double and single bonds are double bonds. You cannot rotate about a double bond. And so what we see for amides is you would look at that and be like, oh, that's a single bond. That nitrogen can rotate freely about that single bond. It can't. That pair of electrons is in resonance, right, being pulled to that carbonyl carbon. And so this nitrogen carbon bond is very rigid. And cannot rotate. And to say that it can't rotate is a little bit of a lie, but it doesn't. It's a fairly rigid bond. This is incredibly important. These amide bonds are really important in biochemistry. It turns out that all of your proteins, all those amino acids are held together by these bonds right here. And so this sort of idea of them being very rigid and all that electron density being pulled onto the oxygen is very important in biochemistry. All right, so we look at that bond and it looks like a single bond, but again, we cannot rotate about that bond as illustrated in our other resonance contributor here. Okay, so then if we're talking about basicity, we're not talking about amides, right? Because the amides don't play the roles of bases. All right, so then let's talk about amines and compare different amines and their basicity. Remember, we can sort of numerically talk about how basic a particular molecule is by looking at the pKa of its conjugate acid. A weaker conjugate acid implies a strong base and vice versa. All right, this amine right here has a pKa around 11, and that is pretty typical for amines. All right. It really doesn't vary too much as you change the structure of your amines, all right, or their classification. By that, I mean we can have primary amines, secondary amines, or tertiary amines. And then like the methyl equivalent of an amine is what's called ammonia. So ammonia is NH3. No carbons bound to that nitrogen. A primary amine means that there is one carbon bound to that nitrogen. A secondary amine means that there are two carbons bound to that nitrogen. And a tertiary amine means that all three of those nitrogen bonds are carbons. All right, and just to compare, this was different than our classification of alcohols because an amine, that is just a compound that has a nitrogen, so it can have any up to 3 bonds. If we were talking about alcohols, we specifically were talking about OH groups. That oxygen can only have one other bond. So a primary alcohol, we were really looking at the carbon that that OH group was on and counting neighbors. A secondary alcohol doesn't mean that the oxygen has 2 carbons. It means that the carbon that it's bound to has 2. Tertiary alcohols. Carbon that it was bound to had 3 other carbon neighbors. All right, so it's a little bit different with amines. Any organic molecule with a nitrogen is an amine. So our classification is saying how many carbons there are that are bound to that nitrogen. All right. So there's a slight difference between the basicity of primary, secondary, and tertiary amines, but there's not like a trend where tertiaries are always more basic or something like that. All right, so for our purposes, we're just going to say ammonia, primary, secondary, and tertiary amines are all about the same in terms of their basicity. Okay. But aryl amines, so for example, aniline, is less basic. All right, the pKa of its conjugate acid is around 5. And again, the stronger the conjugate acid, the weaker the base. So if we got a lower pKa for our conjugate acid, that means it's a worse base. All right, and so why might that be? Okay, well again, to be a base, it's got to be able to donate this pair of electrons in an acid-base reaction. And with that benzene ring right next door, it's got these resonance contributors spreading that negative charge, spreading that lone pair around that ring. All right, so just like we were talking about with amides, these aryl amines, these nitrogens have less electron density than regular amines. And truthfully, there's two others that we can draw that I'm going to get lazy and not draw in here, but we would have a total of 4 resonance contributors for this structure. Just bouncing that negative charge to various carbons within the ring. Okay, and then lastly, we talked about these aromatic, what are called heterocyclic amines. All right, so when we were discussing aromaticity, we of course talked a lot about benzene, but then we also talked about these heterocyclic compounds. All right, and remember these heterocyclic compounds, this lone pair gets to choose if it wants to be in the ring. And we said it would choose to do so if it would make that ring aromatic, right? So then in this case here, if I'm counting my lone pairs in this ring, I got this, or I'm sorry, if I'm counting my electrons in this ring, pairs of electrons, I have 1, 2, that lone pair would make 3, so that lone pair is going to be delocalized around that ring, all right? In fact, this molecule is going to go so far as to sp2 hybridize so that that lone pair is in a p orbital. So this thing right here is just an absolutely terrible base. We're going to just say not basic. All right, in order for that to play the role of a base, it would have to break its aromaticity. It's not going to do that, right? It needs that pair of electrons to participate in the conjugation of that ring so that that molecule is aromatic. If it gets rid of that pair of electrons, the compound's no longer going to be aromatic. That's not a favorable thing. All right, just to sort of prove this point here, the conjugate acid pKa of this compound is about 0. Right? Very, very strong acid, meaning that its conjugate base is a terrible base. All right, so then I want you to rank the following molecules from the worst base to the best base. All right, so which one of these is going to be our best base? A, B, or C? Yeah, the one without any sort of a ring structure that's going to pull electron density away from that nitrogen. So we don't know how to name them yet. But anyways, this thing right here is my best base. All right, so how are we going to distinguish between these two? Because they look pretty close, just different number of carbons. All right, so remember, when we talked about aromaticity, an important part of an aromatic ring is the number of electrons that are in that ring, right? You got to have that odd number of an electron pairs in order to be aromatic. If it's an even number, we call that anti-aromatic, which is bad. All right, so in this case here on the left, we have 1, 2, 3 pairs of electrons. If I added that lone pair, that would make 4. Well, we're not going to do that. We're not going to have it be anti-aromatic. So instead, this lone pair will just not be conjugated into that ring, not delocalized, i.e. sp3 hybridized. But if we look in our other molecule, 1, 2, now that lone pair makes 3. That's good, that's aromatic. So this will delocalize, i.e. that nitrogen will be sp2 hybridized. Okay, so then which one is the better base? The one on the left or the one on the right? Right? The whole point is that lone pair has to be available in that reaction. If that lone pair is delocalized around that ring, it can't be playing the role of a base. So that non-aromatic compound would be sitting in the middle, and our aromatic heterocyclic compound would be the worst base up here. All right. Other fun facts about our amines here. Everybody's favorite topic of stereochemistry. When we were talking about stereochemistry of an alkane, how did we identify a chiral carbon? 4 distinct bonds, right? So if we look at an amine can only have these 3 bonds, but it still seems like, okay, well, if I make them all different, you know, yeah, it doesn't have this 4th bond, but it has this lone pair here, right? It seems like this amine should be chiral. But amines can do this magic thing called an inversion, where that lone pair of electrons magically teleports to the other side of that nitrogen. And so in this way, your nitrogens are always undergoing these inversions, so they wouldn't hold any sort of stereochemistry difference. Right? In effect, you can think of these amines as always converting between their R and S stereochemistry, i.e. they are not chiral. So, kind of best case scenario when we're talking about stereochemistry, we don't have to worry about it. All right, amines, at least at that nitrogen, we might have a chiral carbon somewhere, but our nitrogens are not chiral. All right. So then to round out our introduction of amines, let's do amine nomenclature. All right, we're going to start with primary amines because these are the most straightforward, and then we'll talk about secondary and tertiary amines. All right, our first step is always to find that parent chain. Our longest continuous chain of carbons. When we find our parent chain, we have this new functional group, amines, and the ending for an amine, our suffix, is amine. Okay, we have our substituents. I'm going to add some notes to each one of these categories, our parent chain and our substituents, so I'm going to leave a little space. And we're going to number our parent chain and then assemble the name. Okay, so then if this was our molecule here, our parent chain would be these 1, 2, 3, 4 carbons. I'm going to number my parent chain in such a way that that functional group is on the lowest number carbon. All right. Unlike some of our other functional groups, specifically these carboxylic acid derivatives, the nitrogen doesn't have to be on the end of the molecule, right? So you do have to specify the location of that nitrogen. So this molecule here would be 2-bute for the 4 carbons, and because we're all single bonds, amine. So 2-butanamine. All right, cool. So let's take this same molecule but now we're going to add an extra alkyl group onto that nitrogen, making it into a secondary amine. All right, so step 1, we got to find our parent chain. This process is going to be very similar to how it was with ethers. Remember, ethers have alkyl groups on either side. So what you did was you looked at your ether and you said, all right, I'm going to chop it at that, in that case it was an oxygen, in this case it's a nitrogen, and I'm going to look on either side and I'm going to figure out what my parent chain is. The biggest alkyl group is going to be your parent chain in that molecule, right? So in this case here, my parent chain is going to be these 1, 2, 3, 4 carbons. The other side we're going to treat as a substituent. So this over here is now a substituent, and just like we're going to name it as an alkyl group. So this is just a methyl group on that nitrogen. So longest continuous chain of carbons that's bound to that nitrogen. All right, for our substituent, we'll call it our amine substituent. It doesn't get any sort of a fancy ending on it. We're just going to name it as an alkyl group, right? So this is just named as our alkyl group. So in this case, it was just a methyl group. All right, but then how am I going to build it into my name? How do I indicate where that alkyl group is? If it was sticking off of our parent chain, we would have our locant of our parent chain, the number carbon that it's on, right? In this case here, we're not going to number it. We're going to indicate its location using an N. That is our locant on our nitrogen. So when I build this into my name here, This is N-methyl 2-butanamine. All right, so we number our parent chain to indicate which carbon it's on, but if it's not on a carbon but on that nitrogen, we use that N as if it was a locant, right, to indicate the location of that methyl group. Okay, cool. So then let's do a few examples here. Excuse me. All right, so for this first one, we have a primary amine. We're going to find our parent chain, these 5 carbons. All right, so my parent chain is this pentanamine. Do I have to indicate the location of that amine group? Yeah, right, look, so there was a few functional groups where we like, oh, they're always on the end, so you don't have to. If it's not always on the end, then you have to, right? So if we haven't seen this in a while, just like if this was an alcohol, we would have to specify it was 1 pentanol because there's 2 pentanol and 3 pentanol. Same thing, we absolutely have to specify that this is 1 pentanamine because there's 2 pentanamine and 3 pentanamine, and those are all different molecules. All right, so for this next one here, now we have a tertiary amine. I'm going to find my parent chain. I got to figure out which one of these alkyl groups is the largest. That would be this propyl group here. So my parent chain here is my propanamine. Again, I got to indicate the location of that nitrogen on that parent chain. So that's carbon 1. The other methyl groups are treated as substituents. So these are 2 methyl groups here. Again, we name them just like we do our alkyl groups. All right, the difference is when we assemble our name, we're going to indicate that they're on the nitrogen by putting the N. I got two of them. I got to indicate the location of both of those methyl groups, right? So this would be N, dimethyl, 1-propanamine. All right, and then our last one isn't an amine, but an amide. And I kind of decided at the time when we were doing nomenclature of amides that we had enough functional groups to worry about, so I didn't throw this secondary, tertiary curve at y'all, but now we can see how it extends. Same idea, we're gonna find our parent chain. Our parent chain's going to contain that carbonyl group. This would be treated just as a methyl group, but it's located on our nitrogen, so this would be N-methyl. My amides, I don't have to indicate the location of that amide group, so this would just be butanamide. Right, not amine, but amide. All right, but yes, we can name secondary and tertiary amides using that same idea. The idea that the alkyl group coming off of the nitrogen, you just name it like a normal alkyl group, and you indicate its position with an N as the quote-unquote locant in your name. All right. So then, how do we prepare our amines? All right, so the first one that we would have learned about last semester would be our nucleophilic substitution reactions. These work particularly well with primary alkyl halides. So let's take all right, so amines are good bases and good nucleophiles. Okay, so then everybody take a second, give me my product of this reaction here. All right, my nucleophilic nitrogen attacks that electrophilic carbon, kicking off that halogen. All right, this would be an SN2 mechanism. Okay, so we can take our amine and add it to an alkyl halide, and we get this substitution reaction. This certainly works, but if you were looking to create a specific amine, this would not be the preferred method to do it. All right? So why is that? Let me get rid of my arrows here to just clean things up. There's a problem with this product that we have here, our amine product. And it's exactly with what goes back to what we just said. Our product is an amine. Amines are good nucleophiles. So when we form this amine right here, what it's going to do is just turn around and react with another one of our alkyl halide molecules. So we're not just going to get this one nucleophilic substitution. It's going to keep going and keep going and keep going, and you're going to get a mix of all these different amines. you're going to get a mix of your primary amine, but also you're going to have a portion of the population that reacted twice. So you get a secondary amine, same number of carbons. Or a tertiary amine. Be lazy and do it this way. All right, these won't stop after just one substitution. You get a mix of all possible products. All right, so if I really wanted one propanamine, I wouldn't go about it this way, right? This would give me a mix of a whole bunch of different ones. It's not that the reaction doesn't work, it's that it works too well, and it's just going to keep going and keep going, all right? All right, great. So thank God we talked about what doesn't work. Then how are we going to synthesize primary amines? All right, for primary amines, there's a sort of variation on this method here that works really well. This is what's called a Gabriel amine synthesis. And a Gabriel amine synthesis takes advantage of what's called an azide ion. All right, which is N3 minus. All right, we got these nitrogens all lined up in a row, all double bonded to one another. I want you to take a second and take this azide ion here and fill in any missing lone pairs and formal charges. All right, so my nitrogen in the middle here has 4 bonds. That means it has no lone pairs and a formal charge of +1. My nitrogens are on either end only have 2 bonds. That means I need 2 lone pairs on each of these. And if it's got 2 bonds and 2 lone pairs, that means that they each have a formal charge of -1. So the overall net charge is just -1, but each of my nitrogens is holding this formal charge in this azide ion. And the whole shtick about these azide ions is they are great nucleophiles and terrible bases. So the only thing that they like to do are these substitution reactions. All right, so let's take our azide ion. We're going to react it with an alkyl halide. We're going to get our substitution product. This now has that whole big ol' N3 group on there. All right, and we can reduce our azide to a primary amine using our normal reducing agent, the lithium aluminum hydride. Okay, so this Gabriel amine synthesis here, if we just want to kind of summarize, we'd take an alkyl halide, we would treat it first with that azide ion. These are sold as sodium salts, so sodium azide would be the what you would purchase and use as your reagent. Then in a second step, you do your reducing agent, and then finally that acidic workup. All right, importantly, this creates a primary amine. All right, cool. But what about if I want secondary or tertiary amines? So this works for primary. All right. All right, so in order to synthesize a secondary or tertiary amine, we're going to start with an aldehyde or a ketone. All right, and what do we get when we treat these aldehydes or ketones with an amine? So let's use a primary amine. Everybody take a second. What are our reactions between aldehydes and ketones and these nitrogen nucleophiles? So remember, these are the weird ones. Out of all the nucleophilic addition reactions to these carbonyl carbons, our nitrogen nucleophiles will completely replace that carbonyl oxygen, creating what we called an imine. All right, but once we get to this step here, these imines can be reduced. I don't know why, but in practice they don't use the lithium aluminum hydride, but the sodium borohydride, our other reducing agent. Okay, and this would reduce this to just a secondary amine. Oh, whoops, I have too few carbons. Okay, so we can synthesize a secondary amine by taking our aldehyde or ketone and adding a primary amine to it and then reducing that imine product. If we wanted to instead create a tertiary amine, we'd do the exact same thing. We would just combine our aldehyde or ketone with a secondary amine. All right, the only difference here is in this intermediate. Remember, secondary amines do not create imines. They create enamines. All right, but these can be reduced just the same. To just a tertiary amine. All right, so for primary amines, we use this Gabriel amine synthesis method using that sodium azide and then reducing it. For secondary or tertiary amines, we're going to start with an aldehyde or ketone. And add a primary amine. Then we'll reduce that. For a tertiary amine, we're again going to start with an aldehyde or ketone, but then add a secondary amine, and we'll reduce that enamine intermediate to an amine. All right, cool. So let's just practice our amine preparation here. We're going to synthesize the following molecule. All right, but we got to start with NH3. Well, not NH3. Start with that sodium azide as your only source of nitrogen. All right, so how can we make the following secondary amine if the only source of nitrogen we're allowed to use is that sodium azide? All right, so everybody take a second, see if you can't propose a path here to get from our sodium azide nitrogen source to this secondary amine. All right, so if I start with sodium azide here, right, that implies that I'm going to be doing a Gabriel synthesis. The problem is that a Gabriel synthesis doesn't synthesize secondary amines. It only synthesizes primary amines. But in order to synthesize a secondary amine, I need a primary amine to do it. And I would mix that primary amine with an aldehyde or a ketone. So that's fine. I can use my Gabriel synthesis to first create a primary amine. And then I can convert that into a secondary amine. Secondary amine using that imine synthesis. All right, cool. So I'm going to create a primary amine first. I got these two different alkyl groups on there. All right, so there would be two, in theory, two first steps that we could do here. Either we could use that 3-carbon propyl group as our alkyl halide, then do our Gabriel amine synthesis. All right, that would give me this primary amine. Or I could use my other fragment, that ring structure.
Did you say we're using azide as the standard?
Oh yeah, sorry. No H on there, just the 3. All right, so in theory, I could use either one of these to create my primary amine, but one of these is going to be preferable over the other here. All right, which one would that be, the top one or the bottom one? Yeah, why the top one? Accessibility, and that's especially important because these reactions here, the first step in my reaction are these SN2 reactions here, right? So they are very much so going to be much faster for primary versus secondary carbons. So this method over here, this second reaction down here, we don't want to do that first. We want to first create this 1-propanamine. Okay, and then in a second step, we'll take that propanamine, we'll combine it with our appropriate ketone. In this case, I'm going to need to use my cyclohexanone here. I'll take that primary amine I created in the previous step. Okay, again, that makes these imine intermediates, which I know everybody's like, yes, duh, because I've been studying so hard for that exam 3 makeup. I remember these reactions very clearly. And then we can reduce those amines. This is what we learned how to do today. Into a secondary amine in this case. Cool. All right, so importantly, if we want to synthesize a secondary amine from the ground up, we're first going to synthesize our primary amine using that Gabriel synthesis, and then we can take that primary amine product and turn around and treat it with the ketone in order to get this imine intermediate, which can be reduced to our secondary amine. Cool. All right, we're going to call it there.